Welcome to my channel, STEM Cafe, where we make everything science, technology, engineering, and mathematics comprehensive, assimilating, fun, easy, interesting, enjoying. Today we are going to deal mainly about force. And why we take this topic first is that everything fundamental in engineering, technology is about force. Force causes change of position and so many things. That's why we are treating force. And other things added to it. That's why we wrote momentum, moment, work, and other things. They will still come under these topics. Force, and in our class we said it will be comprehensive and comprehensible. So we treat everything so that anytime you want to handle any topic that's related to force, it will be fun. And I know that when you are talking about engineering, when you are talking about science generally, more than 80% is about the force, because force affects all these things. And now let's start. Force. What do we really see as force? Force is an entity that we can refer to as, we see it as push or pull. Push or pull. Push or pull. And when you push or pull something, what does that affect? It affects the stationary position or the motion. So, force affects the position or motion of moving objects. It can also change orientation of an object or shape of an object. Affect shape of an object. Before we go into what we see about the object, let's talk about when we ask types of forces. We will look at it from these two main perspectives. We see it from the perspective of contacts, where bodies touch themselves to act. Here we see push, pull. And we also talk about field or force field or force fields. So we can talk about magnetic. We can also talk about electrostatic, gravitational, etc. Now, most times we see forces acting from external, but we can also have internal forces. And under this place, we can also look at forces like forces can also be external or internal. We talk about this when we are talking about when the size comes to play, when the size of the body, where the forces are acting on, comes to play. So internal forces can start coming in. But when it is tiny objects that we refer to as particle, we always look at it from external. So in these contact places too, you can talk about action, reaction, thrust, etc. So we can see force affects so many things here. So let's look at effect of forces. Effect of forces. One, it can cause, because you are saying affect the position. That is, if a body is stationary, it can make it start moving. So, one, it can cause motion. Two, when the body is moving, it can change it. It can change the direction or affect the rate. Two, it can cause change in direction or change in rate of motion or velocity. Okay, that's the rate of change of velocity. So, what are we saying? Forces causes acceleration. 3. It can cause distortion of an object. It can cause distortion. Or affects shape of an object. So, there are so many effects that we can experience from forces acting in a place. Now, so etc. So it can cause so many things. But as time goes on, we'll be dealing with all these examples or reasoning. Now we have basic understanding of what force is. You know, if it's another field, they will talk about force as something that is of significance. But in physics, in engineering, in STEM, force, this is what we see as. And force is a vector quantity. We arrive at how the calculation aspect of force after treating momentum. Now let's talk about momentum. Momentum is an entity that is the product of velocity and mass. The momentum of a body is referred to as the product of the mass and velocity of the body. So product of mass and velocity of the body is referred to as its momentum. So we can say M, let's use P, is equal to mv. That is where P is referred to as the momentum. P is momentum. M is mass. And V is velocity. So, in physics, this quantity is very important and it's a vector quantity. Momentum is a vector quantity. It's a vector. That is, direction is very important. Direction is very important. Now, we have now taken us back to the Newton's laws of motion. Before then, let's look at another thing. Unit of momentum is kilogram meter per second. That's the units. I told you we will be able to talk about force easily. Calculation of force. After we had, let's look at second law of Newton. Or second Newton law of motion. Second Newton law of motion. We talk about the quantity referred to as linear momentum. Linear momentum, that is, momentum is straight line. If you look at it, right from his first law, he emphasized on linear, straight line. He talked about a body will continue in state of rest or of linear motion, that is straight line. What is he trying to say? When there is change in direction, when a body moves, either move round, bends, force has acted. So the only time that you can say force is not acting is when the body is moving in straight line with constant velocity. If there is no external force acting on it, or when it remains in stationary position. Now, I will now talk about second law. As you know, it says that the rate of change of momentum is proportional to the impressed force and acts in the direction of the force. So you can see. So momentum, from momentum now, we have been able to derive force. That's why we quickly talk about momentum. And from this, we are able to derive equation for what momentum and force is. We have said that momentum is mv. So change the momentum, that is delta p, is equal to mv minus nu, which equals m into v minus u. But we realize that F is proportional to delta P, which is M into V, which means that F is proportional to M into V minus U over, and you know from my equation of motion that delta V over delta T is equal to A. So F is proportional to N delta V delta T. So F is proportional to N A. So F equals K N A. So A is acceleration. It is very straightforward. So this is the basic equation for motion. And when they are trying to create the unit for motion, they realize that somebody has done a great work about force. And who is that person? Newton. So they have to give it Newton. But they said, now, what should the K be? They realized that, okay, let's make K 1. K to be equal to 1. And F will be equal to 1 Newton. When M equals 1 kg and A equals 1 meters per second squared. So, 1 Newton will be a force that causes acceleration of 1 meters per second. Acceleration of 1 meter per second squared for a body of mass 1 kg when there is no hindrance to the motion. That is force. Now we have been able to derive the basic equation for force. Therefore, F equals to NA. So now we have achieved two things. We have said that the momentum P is equal to mv. F equals to ma. You can see. And the two of them, they are vectors. In the derivation of the equation for force, we can see that F equals mv minus u over changing time. So F delta t is equal to m into v minus u. Another thing is coming on. So F delta t is referred to as the impulse. And we always talk about impulse when this time delta t is very small. So it creates large force because of that time acting on this. How do I mean? When the force acts, it's always very huge, and its impact, it causes what we refer to as impact. It causes impact. That is force acting within short time. We get there. So this comes up, this impact comes up in collision. We get there. In collision. Now we have talked about collision. Let's quickly go to another small law. And the law is referred to as law of conservation of linear momentum. So, here we are talking about collision. It's talking about in a closed system. Where collision occurs, the momentum, total momentum, please, before collision is the same as total momentum after collision. And what do we refer to as closed system? We are talking about, when we talk about closed system, we are saying that no force is not coming into play, or it is releasing force outside. That is, no work is gained or lost. That is no external force is acting on any of the bodies. So what we are saying here is that when collision occurs, the bodies, the total momentum before the collision will still the same after collision. Mind you, they are vector quantities, and when you are adding them, you add as vectors. We have known how to add vectors using triangle, using parallelogram, or resolution of the vectors. So with this, we have been able to talk about, we can now talk about impulse and impulsive forces. We have already shown what impulse is. That is F delta t is the same thing as the change in momentum. But when we are talking about impulse, we are talking about collision that occurs in a very short time. Collision occurs in a very short time, and force resulted is huge. So we have huge force as a result. So this force is referred to as impulsive force. The resulting force is referred to as impulsive force. So you can see, from momentum, we have been able to generate force, we have been able to generate impulse. Let's now talk about situations that can come up in momentum, since we are talking about collision now. Now let's look at the possible situations of momentum that can occur under momentum calculation. Situation 1. Now let's look at different situations. When two bodies collide, they move in the same direction or in opposite direction, because we've talked about. So here, when this body U1 collides with another body N2 U2, they can move in the same direction or in opposite direction. They can either stick together or they move in different directions. Let's talk about when they stick together. One. Here, finally, they have M1 plus M2, and they have a common velocity V. So here is when they join after collision. So from the law of conservation of momentum, we will be able to say M1 U1 plus M2 U2 is equal to M1 plus M2 into V. You can see. Another situation can occur like this. When they collide, and after collision, they move in separate ways. So we'll be able to say M1 will go with V1 and M2 will go with V2. So we'll be able to say M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. You can see, it's very interesting. So with this, you can substitute and get whatever quantity you have to look for. This is this one I want to talk about is very interesting. It is where we talk about explosion. Situation 3. Explosion. In this instance, we are talking about a body that separates, that breaks up, like when you have a gun and a bullet. Gun and bullet. You know, the gun and bullet initially have momentum that is 0. So when the bullet is released, there will be a recoil on the part of the gun. So initially it will be like this, and the bullet will be inside. So later on, when the bullet leaves, the gun too will go back. It will go like this. Why? Because the initial momentum is equal to 0. So let's ascribe let's say mg, mb, vb for the bullets, and then ug for the gun. Initial momentum is 0. Is equal to mg ug plus mb ub. So if we know the velocity of the gun, we know the mass of the gun, and we know the mass of the bullet, you can easily know the mass of the velocity of the bullet. And because they move in opposite direction, that's why we are going to have it like this: mg ug is equal to minus mb ub. You know, I stated before that direction is very important in all we are doing. Before we go on, I want to give examples of impulse on impulse. We talk about baseball and bats, billiard balls, those situations where force acts, even soccer, yes, the foot and the ball, soccer. You can see that two bodies that are separate come together. But when we are talking about explosion, we talk about bombs, scattering, gun, shots, radioactive disintegration, radioactive disintegration. So you can see, when I talk about explosion, it means a body that is now broken into sizes. A body as a whole now separating into sizes. That's when we talk about explosion. For impulse, we talk about two bodies coming together and then separating. The bodies come together, two bodies come together, and they later separate. Sometimes you might have situation where a body can come like this. Let's say M1, U1, and it goes to meet another body, N2, U2. One of them can go like this. M1 can go like this, V1. N2 can go like this, anyhow, anywhere. What we are talking about is that the direction must be considered. So the total momentum must be the same in that direction. In the direction at which this momentum is taken, it is important you consider the direction. Like this one, assuming this one is, okay, let's say M1, U1, M2, U2. This one goes like this. So the total momentum here will be M1, U1 plus M2, U2. That is initial momentum. And it must be the same thing as this. So let's give this one theta 1. Let's say this one is theta 2. So you have it like this. M1, V1. You can see theta 1. So here, theta 2. M2, V2. Because the sum of these two should give us this one. The sum of these two should give us the initial one. The same thing happens even in explosion. And when we see the examples, you will know. So please put that into consideration always. It is not always in straight line. It can go at different direction from the initial direction that you started with. So please take that into consideration. Another terminology we come across sometimes is coefficient of restitution. At this stage I won't derive it. Later on at higher level, but it might come out in your objective or whatever. When you see something like this, it means, so let's define it. Coefficient of restitution. E is equal to minus relative velocity after impact over relative velocity before impact, which is minus V A minus VB over UA minus UB. It can also be minus into VB minus VA over UB minus UA. A. So another terminology you might come across later on. We'll show the derivation and how to get it. We are talking about another aspect now, elastic and inelastic condition. We know that there is a law of conservation of linear momentum. It's observed under our collision. But there is something that might not happen necessarily. It is the conservation of kinetic energy. That's what differentiates elastic and inelastic collision. In elastic collision, kinetic energy before collision is the same as kinetic energy after collision. But in inelastic, kinetic energy before collision is not the same as kinetic energy after collision. They are not the same. Now let's talk about kinetic energy. In explosive bodies. In explosion. Kinetic energy in explosion. You know what I have said? In explosion, it's a body that disintegrates, that breaks apart. The simplest example that comes to mind is that of bullet and gun. Let's say mg is mass of gun and mb is mass of bullet. You can see. So when there is explosion, that is when the bullet is shot, as you have seen before, it's mg ug is equal to minus mb ub. The two are equal. Let's now look at another thing. What is the kinetic energy of gun? Let's say KEG is equal to half mg ug squared. Kinetic energy of bullets, half mb ub squared. But if you look at this, you can call this one P, because P for both are equal. Now let us see what P will be. Let us express the kinetic energies in terms of P. If you look at this, it's going to be half mg ug squared. So let's square this over mg. You can see. And this one too will be half mb squared ub squared over mb. So we can see this as p over 2mg, and this one too will be p squared over 2mb. Now you can now see that, okay, let's do something again. So KEG over KEB will be equal to P squared over 2mg times 2mb over P squared. This one cuts this. This one cuts this. Therefore, the ratio of the kinetic energies is inversely proportional to the masses of the bodies. What I mean is, the ratio of the kinetic energy of the bullet is inversely and the gun is inversely proportional to their masses. So if you want to find, if you know the energy of one body, you can easily calculate the energy of the other body by noting that it is inversely proportional to the mass of the body. That is it. So when we get to further calculation, you will see how interesting all this and the application in different levels.